Today's webinar is presented by Sheetak Inc. and hosted by Photonics Media. Today, you're going to hear from Ian DeFilippi, who is the Director of Product Management at Sheetak. In this session, he is going to share an introduction to Sheetak, a showcase of their current thermoelectric products, and a preview of their groundbreaking silicon-based thermoelectric architecture. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this online after the presentation, and you will receive a link to that recording by email. So with nothing further from me, I'd like to welcome Ian DeFilippi. Welcome.
Joanna. I'm Ian DeFilippi. I'm the Director of Product Management at Sheetak. As I was saying, we are going to discuss the fundamentals of thermoelectric technology, the advances that Sheetak has made for the industry, and applications for optoelectronics using thermoelectric cooling. Thermoelectrics are a class of materials that convert temperature differences into electrical voltage and vice versa. The property of applying electrical current and obtaining heat and cooling is called the Peltier effect. On the opposite side, the phenomena that converts temperature gradients into voltage is called the Seebeck effect. We're going to concentrate in the former for electronics. Overall, there are a few goals that design a better thermoelectric device. Find a material with high Seebeck coefficient, that can generate higher voltages than differential, and design a device that allows higher electrical conductivity with lower thermal conductivity. A few key metrics are important for thermoelectric coolings. The Qmax, or cooling power, is the maximum cooling allowed when a delta T is 0. Typically, the actual cooling load is in the range of 1/3 to 2/3 of the Qmax. To increase the cooling power of a device, a designer can increase the number of thermoelectric couples. The delta T max is the maximum temperature differential a TEC can develop when a Q is equal to 0. To achieve an efficient operation, delta T is in the range of 1/3 to 2/3 of the delta T max. Some companies stack modules on top of each other like a pyramid to achieve a higher delta T. This is commonly known as a multi-stage TEC. A COP, or coefficient of performance, gives us how much power a device needs for certain cooling power. We can think of this as a system measure. So in order to have the highest efficiency possible, we have to select the right device for the right system. There are other key metrics that are more operational and part of the requirements of each system. A TC module works with, first, as a baseline, two types of semiconductor elements commonly arranged in series. The right materials first are doped for an enhanced Seebeck coefficient. Then these T legs are sandwiched between two ceramics, usually made of aluminum oxide or aluminum nitride. In a cooling system, we want to maintain the temperature differential between the hot side and the cold side in order for the device to keep operating efficiently. So the goal, again, is to increase the electrical conductivity and reduce the thermal conductivity. Why are thermoelectric coolers used? Basically, we can mention a few factors. Thermoelectric coolers are made with solid-state materials. That means no moving parts, which reduces the chances of mechanical failures. It can also be mounted in any direction. The small sizes are ideal for spot cooling at the specific parts that need to be cooled. The technology enables very precise temperature controls in the order of tenths of a degree. It also allows cooling at temperatures well below ambient. And because there are no gases used, it is very environmentally friendly. I'm going to describe how a quick overview on how TC modules are made. First, raw materials are ground into powders, then so melted, and then create put together as a puck or bowl, then saw into wafer discs, and these wafers are electroplated and diced to create finish legs. These finish legs are then placed and soldered into ceramic substrates. Finally, some wires are attached in order for to integrate into into the desired system. There are many steps involved here. Often, some of them are manual, and involves when it involves processing raw materials into final products. The current state of the thermoelectric industry is that there have been limited advances in practical TE materials over the last 30 years. Basically, they're still using the same bismuth telluride materials in these last 30 years. There has been marginal improvements in design and manufacturing processes for TE devices. The current state in the industry makes it very costly to develop and deploy technology to keep up the trends of reducing size and increased power efficiency. For the last 12 years, Sheetak has been working on building a new paradigm in the thermoelectric industry. We are a company that pushes the boundaries of thermoelectric technology and systems. We count with a great team of material scientists, veteran semiconductor professionals, and very talented application engineers. Our founding team has been working on thermoelectrics for over 20 years. We hold over 25 patents in key areas of thermoelectric technologies, devices, and systems. We have great expertise in optimizing material composition, system design, and volume manufacturing. Centum C3 is our family of single-stage and multi-stage conventional TECs. We go from sizes from 20 by 20 millimeters to 60 by 60 millimeters. In particular, our flagship two-stage TEC, compared to our competitors, we have accomplished to remove the ceramics in the middle and replace them with copper links, while still reducing the thermal conductivity. With this design, we deliver a higher delta T with higher cooling power and a larger cooling surface in a thinner device. This is a two-stage TEC performing like a three-stage TEC in the fourth factor of a single stage. It is truly impressive. Our applications and manufacturing engineers work closely with our clients to adapt our modules to the needs. We have done a lot of great work in this line, and we are very happy to discuss potential applications not seen elsewhere before. We do our design and volume manufacturing here in our plant in Austin, Texas. A few months ago at OFC, we announced CoolChip, our new true thin film technology microcooler, a first in the thermoelectric industry. This delivers unprecedented cooling performance in very small geometries. CoolChip microcoolers have a broad market appeal in photonics, optoelectronics, data centers, refrigeration, medical, and industrial applications. Compared to bulk materials, thin film geometries is in the micron scale, whereas the bulk materials are normally in the millimeter scale. Thin films are generally deposited onto wafers using wafer scale semiconductor manufacturing. Processes like PVD and the finished wafer um, has sorry. Thin films are deposited onto wafers compared to bulk devices that are pick and place into ceramics. Our cool chip, a 1.2 by 1.8 millimeters and only 0.3 millimeters thick, with 16 thermoelectric couples, offers a Qmax of 1 watt over 1 watt at 25 degrees C, and a delta T of 74 C. Optionally, we can add the top lid for heat spreading, or design a flip chip implementation to bond directly to the device that needs cooling for an even smaller footprint. There are some clear advantages of using a thin film implementation of a thermoelectric cooler. The geometry makes it ideal for spot cooling solutions. We deposit our materials and seal our metals during production. That means no soldering or exposed junctions, which increases the reliability of the device. As we'll soon see, a thin film implementation allows the couples to reach the target temperatures in less than 1 millisecond, compared to 30 to a minute for a conventional device. Depositing materials enables us to build a very couple dense product, which means high cooling density in a very small form factor. Because we eliminate pick and place with deposition, we can scale down the size of the devices but still produce at volume quantities. And compared to anyone else in the industry, we source all of our raw materials in the US. All of our production is done locally. Our thin film device is built using advanced semiconductor techniques, like wafer scale processes with high precision and is highly automated. We start with a silicon substrate. We deposit the metal interconnects, TE materials, barrier metals directly onto the wafer. The wafers are then diced into the final chips and used directly or assembled into our requirement combinations. This is a solder-free precision manufacturing, and the elements remain hermetically sealed. Optionally, we can add a top lid again for thermal spreading. This is a finished cool chip without a top lid from our latest finished lot. You can see the device all plated with NPIC. On the left, you can see the wire bondable pads, and on the right, you can see the 16 NNP couples, all plated. To show you one key advantage on how this technology is superior to conventional technologies, you can see how fast this device responds when applying current. Some applications require very fast reaction times, like PCR coolings. We can observe here an immediate condensation getting formed on the junctions in less than 1 millisecond. Some applications for optoelectronics, we know that the trend is always going to be to build smaller systems and more power efficient systems. Lasers, for example, require very precise temperature controls to prevent wavelength shifts. This is hard to obtain with other cooling methods. In optical transceivers, for example, the TOSA, or transmit optical subassembly, holds a laser diode that is used to convert electrical signals into optical signals. Generally, a TEC-based microcooler is used to maintain the temperature stable. A cool chip can be mounted on a TO-CAN or a butterfly package that can act as a heat sink. A TEC with the right dimensions is ideal for very precise and power-efficient spot cooling. Other laser-based applications would benefit from this principle, like pump lasers, ladder systems, and we also foresee that cool chip would be a great addition to the co-packaged optics silicon photonics stack, especially in systems that have laser integrated. Imaging sensors like CMOS, CCD, and infrared are all highly sensitive to temperature increases. Quality degrades rapidly for in phone cameras, AR, VR devices, or biomedical applications. One example of these challenges is the dark current noise. Light and heat both create signals in sensors, but sensors can distinguish the difference between thermal electrons, cannot distinguish the difference between thermal electrons and photoelectrons. That makes the thermal system contribute as dark noise, degrading the quality of the image. This is especially critical in long exposure, for example, under low light conditions. Very fast cooling, a high temperature differential would definitely will make a difference and provide a significant advantage in terms of quality of the image, performance, and the reliability of the product. As we can see in this image, we can create an array of cool chips to build an imaging cooling sense system. For applications with very high cooling power needs, we've developed EON, a TC module with the highest couple density in the industry. There is nothing to compare that in the market right now. 506 couples in a 7 by 7 millimeter square with only 0.4 thickness. With over 30 watts, it achieved a Qmax of 30 watts, comparable with a device 9 times its size. We are able to adapt this cooling density to the system requirements. For example, industrial lasers need to cool in the tens of hundreds of watts to maintain thermal stability and high cooling power. This is a great spot cooling complement to advanced cooling systems used that are currently used to reject the heat, like liquid cooling, for example. EON would also be a great use of for energy harvesting using the Seebeck effect, but that's a talk. That's a subject for a different talk. We are very happy with our development and are currently taking sample requests at the moment. Thank you very much for your time, and we're happy to answer some questions from you all.
Thank you so much. And yes, everyone, we have time for a few questions before we close. If you have not already, please go ahead and type your questions and comments into that webinar chat there. All right, so let's see. This first question I have here, Ian, is what are the size limits in dicing and placing bulk element geometry?
With bulk materials, the size limit is kind of limited by the method that's used to dice. So typically, it's either wire saws or blade saws. So when you start getting below, like 200 microns in X and Y dimensions, the material can fracture and basically you get a lot of yield loss. So typical bulk material sizes, are on the order of 300 micron by 300 micron and maybe a half millimeter thick. In some cases, they can be a little bit thinner. But because it's a very mechanical process to cut the materials, the smaller you tend to go, the larger the yield loss you have, which drives up the cost of the assembly. And then when you try to do automatic pick and place equipment, the smaller the leg geometry, the harder it is to adapt some of that automated pick and place equipment for placement of these really tiny legs. So in some cases, those processes are still done very manually, which again also increases the cost of the assembly. And that's much different than thin film. Thin film, it's deposited directly on the wafer through masks, and these masks are cut or etched in very precise geometry and can have very tight placements and very small geometry. Element sizes can be 20, 30 microns in diameter, and the thicknesses are on the order of microns. But because of the semiconductor manufacturing technology that's used, you don't end up having the same challenges scaling down with thin film technology as you do with the bulk technology.
Great, thank you so much. All right, let's see. This next question we have here is, can you describe the difference between bulk and thin film thermoelectrics from manufacturing perspectives?
Yes. So in bulk, um, I explained a little about bulk manufacturing that we you can grow the raw materials and then dice them, uh, well, saw them and then dice them and then pick and place. In bulk, sorry, in thin film, what we do is deposit them directly into substrate. And these like layers after layers of metals and T materials and sealants until we build the thermoelectric device.
Great, thank you so much. This next question is a little bit specific, but they're asking, what is the part number for the TEC you showed? 7 times 7 millimeters with Qmax is greater than 30. They're asking in case they wanted to place a sample order.
Just you can refer that just as Eon. There's only one. We have one final product in that series.
Perfect, thank you. This next question is, what are the sizes and cooling power for the initial QOOL chip products?
Can you repeat the question, please?
What are the sizes and cooling power for the initial, is it QOOL chip products?
Yes, it's 1 watt of cooling power, and the device is 1.8 by 1.2 millimeters and a thickness of 0.3 millimeters.
Thank you so much. All right, this next question is, are there any size limitations for the Centum C3 products?
Oh, uh, there are some limitations when we really go to very, very small form factors. Currently, what we feel very comfortable are anything above 20 millimeters by 20 millimeters.
Thank you so much. And this next person asked, is there an expected cost difference between thin film and conventional products?
There is really no like big difference. Uh, I think the bigger difference will be when we scaled up for volume manufacturing, and we expect this because of the ways that we build these devices. They're gonna scale up very nicely, and we can see like a significant cost reduction.
Wonderful. Thank you so much. And everyone, I think that's all the questions we have for now. But if you do think of another question, you can let us know. By emailing webinar@photonics.com. That's webinar@photonics.com. You can also request a copy of today's slides at that email. And just a final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording by email. Actually, I do see a few more questions in here. Ian, are you okay if we take maybe one more?
Yeah,
Sorry about
absolutely.
that. Of course,
Yes.
great. So this last question that just came in is, what is the upper operating temperature?
See. For both the Centum C3 line, it's depends on the solder you use for that. So typically, the highest temperature there is like a sac-based solder, so on the order of like 200 C. For the thin film devices, because there's really no solder used in the core assembly of the device, and for say the top, the heat spreader or the top lid bonding, we typically use like a gold tin attachment method there, or maybe even other higher temp attachments. The range can be higher, maybe higher than 200 C, but maybe less than 300 C. And then with the thin film product line, we do have other materials kind of in our roadmap in the future for say high temperature energy harvesting and things that can even go higher than that. But those aren't kind of commercially available at this point yet.
Wonderful. Thank you for that. And thank you everyone for sticking with us with that. So that is all we have for today. And I'd like to thank Ian one last time for presenting with us and thank everyone for participating. This webinar is presented by Sheetak and hosted by Photonics Media. So thank you, everybody. Have a nice day.
Thank you, John.